We've talked about momentum conservation in one-dimensional collisions. Train cars running along a track, banging into each other, things like that. But we know that collisions can take place in 2 and even 3 dimensions. Well, let's look at a 2-dimensional situation here. Let's pretend we're looking down on a pool table, a billiard table, and the ball is getting hit. The black ball here is getting hit to the right, and the red ball, ball number 2, is sitting there at rest. And afterward, what's going to happen? Afterwards, ball 2 is going to be going up and to the right, and ball 1 is going to go down and to the left because it strikes ball 2 off center, a little bit below the center point. So let's take a look at this situation. We know that momentum is a tool we use for getting through a collision problem. So the initial momentum has to equal the final momentum. These are vector quantities. And when we have vector quantities, one of the first things we like to do, a 2-dimensional problem with vector quantities, is break it up into components. So if the initial momentum equals the final momentum, then the initial momentum in the x direction will have to equal the final momentum in the x direction, and the initial momentum in the y direction will have to equal the final momentum in the y direction. I'll define the right as my positive direction and up as my positive direction. Initially, we only have x momentum. In this particular problem, we have the mass of object 1 times v1 initial. It's going in the positive direction, and that has to equal our x momentum at the end of the problem. At the end of the problem, I have the mass of object 1 times its velocity in the x direction, and the mass of object 2 times its x component of its velocity. So that's where the cosine thetas come from. We need the x component only of the velocity. So there's our first equation. Our second equation comes from the y direction. Initially, there's no momentum in the y direction. And at the end, I have m1 times v1 final, the y component of v1 final. And I have m2 times the y component of v2 final. And since up is positive, I get this m1 times a negative v1 final sine theta 1. And I have a plus m2 v2 final sine theta 2, because m1 is moving in the negative direction and m2 is moving in the positive direction. Here's my second equation. 2 equations. Hopefully there's only 2 unknowns in the problem, and we can solve for what it is they're asking for. Maybe they're looking for the 2 angles, or maybe one of the velocities and the angles is given and we're solving for the other velocity and angle. But we have 2 equations we can solve for 2 unknowns. Sometimes with these problems, like with the billiard table, they'll tell you that the collision is elastic. If the collision is elastic, then we can get one more equation. We know that the kinetic energy initially has to equal the kinetic energy final. So in this particular problem, I have a 1/2 m1 v1 initial squared. m2 is not moving, so that's all of my kinetic energy of the problem. At the end, I have a 1/2 m1 v1 final squared, and I have a 1/2 m2 v2 final squared. So that would be a third equation, and then I could solve for 3 unknowns. If you're told it's elastic, you can go ahead and use that. If you're not, don't assume it's elastic just because the objects bounce off each other. So that's two-dimensional momentum. Basically, same as one-dimensional, you're splitting the momentum up into its components. X direction, momentum has to be conserved. Y direction, momentum has to be conserved. And so we can go ahead and do the problem this way. This is true if there's no external force acting in either of those directions. As long as there are no external forces in the x direction, then we can say the initial momentum and the final momentum will be the same. And as long as we don't have any external forces in the y direction, we can say the same thing. Sometimes we get problems that look like this. We have a cart with mass m2, maybe it's at rest, and we have a ball or something, a big chunk of clay, and it's going to be thrown with some initial velocity at some initial angle into the cart. So at the end, what do we have? We have a cart with a big lump of something stuck in there, and the cart's going to be moving. So in this problem, what we would say is that the initial momentum in the x direction and the final momentum in the x direction have to be equal, because there's no external force acting on our system in the x direction. The cart is free to move back and forth in the x direction, and the ball is coming in, or the lump of clay is coming in and hitting. Nothing is acting on this system in the x direction. But we would not say that the y direction has momentum conservation because the Earth is interacting with our system. We would ignore the y component of the momentum and only look at the x momentum. So let's do that. Initially, if the cart is at rest, we only have m1 times v naught cosine theta. I'm calling to the right my positive direction. That's the x component of the clay. And at the end, the whole thing is stuck together, and it's moving with some speed v final. So now we can solve for v final. And we have our answer. The important thing to note is, in the x direction, we could use our momentum conservation laws because there were no external forces affecting the motion in that direction. In the y direction, there was the Earth in the way. Can't say that momentum is conserved in the y direction because the Earth basically has infinite mass as far as we're concerned. We can't measure any change in the momentum in the y direction of the Earth. So we wouldn't use momentum in the y direction.